Good morning, everyone. Today I will introduce our work on high-frequency telemetry for SONiC, which bring real-time and high-resolution observability to the AI data center. So here is today's agenda. This talk will introduce the following part. The first part is about the motivation, why high-frequency telemetry is critical to the AI scenario. Actually, in the previous meetings, some experts from such as Microsoft and NVIDIA have introduced why we need the high-frequency telemetry. If you miss that meeting, I will provide a very simple recap. And then I will introduce why the current SONiC telemetry solution cannot support the high-frequency telemetry. Then I will also introduce our design about some challenges we encountered. What's more, Janet will talk about some advantages of our ecosystem and show a demo. And finally, we can see our roadmap as well. So here is our motivation. First, let's find what is the high-frequency telemetry system. High-frequency telemetry system is such the simple rate with such as 10 millisecond to the 10 microsecond to 10 millisecond, and they maybe have a more telemetry data need to be collected and more ports, such as more than 500, even to the 1,000 ports in one switch, maybe in next generation, and both of them are the requirement of the AI data center. So the following screenshot is from the last year's OCP Global Summit. The expert introduced why the high-frequency telemetry function is critical needed. Not just nice to have, it's critical. As you can see, in a traditional telemetry system, maybe within 1 second interval, the bandwidth graph often looks like a flat line, and many detail and optimization opportunity may be hidden. So it make it impossible to tune or some debug our training system without the high-frequency telemetry. But with the high-frequency telemetry system, such as 1 millisecond pulling or sampling interval, we can see some spark or some cliff in the bandwidth graph. Based on this simple way, maybe we can tune our system. So here's our motivation. So now let's say what the why the current SONiC telemetry cannot support the high frequency telemetry, and what is the current limitations. The first, I believe, and the key issue is about the too heavy telemetry stack. So as you can see, to the existing counter collection flow, as now as the flex counters is initiated from the SYNCD and call the side API to convert the side query, the face query to the vendor's SDK, and then vendor will query some registers in the ASIC. But maybe some different counters have some different optimization in its SDK, such as cache, some counters, or some others. But the above steps I mentioned cannot be skipped. So the whole stack is too heavy. Meanwhile, it is the current solution is just a single thread architecture, which means it is not suitable to the current more and more port scenario. What's more, we store in the current solution, we store every counter into our counter DB, because as you know, the SONiC is based on the Redis. We based on Redis to manage it and to monitor it. It means it isn't ecosystem friendly enough. If we want to use a different monitor platform, such as we want to use some FlexDB or some Prometheus system, we cannot. We have to develop a new adapter to it. So here is the current issue. Here we go. Here is our solution, high-frequency telemetry HFT. The most important change is we change the mode from the pull mode to the push mode. It is very straightforward idea. We reduced the size stack from the telemetry platform. It means we no longer use the SONiC to transmit the telemetry data. But we will still use the site to manage the HFT system. We will to create some HFT objects based on SONiC as well. So just separate the telemetry system from the to the data plan and the control plan. Control plan still use the site to management it, and the data plan we use this new architecture. And then the next idea is to leverage the core processor of the ASIC. The core processor in different vendor may be different things. To some vendor, maybe it is ARM core. Other vendor may be MCU or something else. So we use it to organize and to push data. Meanwhile, in our design, we introduce a new processor, it is a core processor named countersync B. We design it as a multi-thread, and it can be better take advantage of multi-core. So in summary, the second point is to fully utilize the resource and the hardware performance in our architecture. And then our design is also backward capabilities, because we will also write the counters to the counter DB as well. But we have a new and a better exporter of open telemetry collector for better ecosystem integration. Here let's say the challenges when we develop the high-frequency telemetry. The first thing is about the CPU bottleneck, which means the single core performance cannot solve the collection work of many ports, such as more than 500 ports, as mentioned. And so we have to leverage multi-core. And the second challenge is vendor diversity. What that means, which means even to a same counter, such as ingress packet number, their weight are different across different vendor or ASIC. For example, to a vendor A, the native counter maybe is 32 bit, but to the vendor B, the native counter may be only 24 bits, and the sampling frequency support is different as well. Actually, here is a very interesting thing that we can see. We find some vendor not only define the upper pulling, the lower pulling interval, but also define the upper limitation. Upper limitation means a vendor announce they can only support such as 10 milliseconds pulling interval, but cannot support 100 milliseconds pulling interval. That's very interesting thing we find. This is because the counterweight is a limitation. For example, here I provide an example. The first row is the timeline, and the second row is about the native counter value in different time point. We have this example includes two simple rates. The first simple rate is 3 milliseconds, and the second one is 10 milliseconds. As you can see, this counter happened 3 times overflow. If the simple rate is 3 milliseconds, we can recover the exact number of the counter easily. But if the sampling rate is 10 milliseconds, we cannot recover the data, because we don't know how many rollover happened during this time. So that's why some vendors ask upper limitation of pulling interval. And then the last challenge we encountered is about the weak ASIC coprocessor, which means we cannot expect it can do everything what we can do on the host CPU, such as the x86 platform. The CPU power is too weak. The core processor power is too weak. So let's say how we deal with these challenges. Here is the core processor I mentioned, counter syncd. We use the Rust and actor architecture to implement the counter syncd, which means multiple actors will be running on multiple CPU cores. And it is easy to add more actors for parallel if you find some bottleneck. For example, if you find the IPFix parser is too slow, we can add more IPFix actor easily. From this graph, okay, from this graph, this font is too small. Okay. Here, this part is SWSS actor. SWSS actor will be used to receive the configuration of the for the HFT, and here actor is the netlink actor. Netlink actor will receive the telemetry data sent it from the kernel module. The kernel module will provide by the vendors, and then we will have a dedicated actor. This actor is the IPFix actor. It will be used to pass the IPFix message sent by the vendor. And we have a dedicated actor named harmonize actor to handle the counter rollover and to resampling to unify the telemetry frequency so that the backend service will not be aware of the vendor diversity. Finally, we add a new export here to convert the telemetry data to the open telemetry message. Let's say some detail about our data format. We choose the IPFix as our data format. So maybe someone will maybe ask a question why we don't use such as JSON or buffer, because they are more popular. Because for JSON we think it is not efficient, which means it have too many useless characters such as comma or some bracket. And to a pro buffer, it is very good format, but it is very hard to deploy in the kernel or be deployed in the ARM core of the ASIC. So we didn't choose that format, which can the advantage of IPFix is it is part or decoder is very easy to implement it. Maybe just 100 line code can implement it the encoder or parser of IPFix. And maybe someone is not familiar about the IPFix. I will give you a very simple introduction about IPFix. IPFix is someone like a proto buffer. It has two kinds of messages: the template and the record. The template is such as the proto files. It will to describe or explain the binary, such as a proto file, and the record message is just a binary message, such as the proto buffer binary message as well. And we encode our site tab and state ID to the IPFix template, so that we can, if we got a IPFix record and it is the template, we can restore the original site tab and state ID to now with content the content meaning. We can easily recover that. And here is the example of the IPFix record. We only have two fields, such as the template ID which will be used to point which temperature we will use. And another one is just the length to describe how many bytes in this record. Except this two field, other bytes are fully meaningful for the telemetry state. And we provide a proposal to the vendor how to push the data to the user space and to our CountSyncD processor. It is just a proposal. The different vendor can implement different can have different implementation. We assume they can leverage their MCU or ARM core to collect the state on the ASIC and send the DMA event to the kernel. And then DMA message will be included in a RAM buffer because we are keeping the kernel because we hope if our CountSyncD crashes, like a process is unexpected exit, it can help us to hold some data during a CountSyncD crash. And then kernel module will push the IPFix message into a netlink, which means we use the netlink to do the communication between the kernel with our user space. Finally, we really hope more and more the DMA engine and the netlink module will also be provided by the vendor. And we really hope more and more vendors can support our HFT feature if they have the capability to do that. And about the open telemetry part, Janet will take over and introduce the rest.
Thanks. So I will continue. Let's continue by looking at the open telemetry messages. As so mentioned before, the IPFix messages will be converted to open telemetry messages in CountSyncD. To make HFT compatible with modern observability systems, we built it around the telemetry. The OTel collector runs as a Docker container and is responsible for receiving, processing, and exporting metrics. And it supports multiple backends such as InfluxDB, Prometheus, or Azure Monitor through a unified open telemetry protocol format. And this gives us a vendor agnostic pipeline, which is scalable, flexible, and easy to maintain. And this graph shows that the reason why we chose the open telemetry collector. Without the OTel collector, each backend would require a custom integration, and it also requires different data formats, and it's not in a unified way. And it's also have a separate monitoring pipelines if the customer wants to change the backend option. And with the open telemetry collector, everything becomes simpler. We only need one integration, and the backend changes can be made by configuration only. And it's a standard and sustainable pipeline for telemetry data. And this is a visualization interface of InfluxDB. In the demo, we will show how to enable HFT on a SONiC device. And you can configure telemetry parameters through RedisDB. And here, the first command we set 1000 microseconds, and with the HFT feature enable. And the second command shows that we're inserting data to config.db, and we set we configure a profile name and object type. Here we chose port, and you can also set it as queue or priority group, etc. And we also set a stats name here. And the ports we wanted to monitor are these four ISNets. For example, ISNet 64, 72, 80, and 88. And then the next step is to start the open telemetry collector and the InfluxDB service using Docker Compose, and then launch the countersync process. For demo purpose, we set up the OTel collector and InfluxDB inside our SONiC device. It can also be deployed as an outside endpoint. And countersync feature has not been released yet, so we start it up manually. In the future, we expect this to be in the service in our SONiC environment. And finally, if you choose InfluxDB, you can visualize the real-time statistics on the website interface like this, just in a few steps.
Skip.
The time limitation, we might skip the demo for today, but we gave a demo a few days ago in the SONiC demo booth. Looking ahead, we have a clear roadmap. In phase 1, by the end of 2025, we plan to implement core HFT functionality and support key AI data center status such as stats such as port queue, ingress, priority group, and buffer pool. Here are some counters we have implemented and will support. And in the phase 2, mid to late 2026, we plan to migrate 95% of SONiC stats to HFT floor. And in the currently, if any of the in phase 3, currently, if any monitored objects is updated or added, the existing HFT will be interrupted and regenerated. So in the future, in phase 3, we hope to support dynamic monitoring updates without data loss. To wrap up, HFT provides low latency, high throughput telemetry for AI data centers, and it's built on an optimized architecture. As I mentioned, it's a push-based, multi-core, and coprocessor accelerated. And HFT also use efficient IPFix encoding, and it integrates seamlessly with open telemetry and gives us a vendor agnostic way and a future-proof telemetry solution. And thanks all for listening. And now we're happy to take any questions.
Hey, just wondering if we can collect transceiver information. Let's say it's like, let's say ID information or any sort of information from the hardware. I know that those site support is not there, but would it be a good idea to collect them? Is it possible at all?
So which kind of information? Which kind of information from hardware?
Like transceivers, the optics. Let's say I want to find reasons for a port flap or.
I'm not sure, because according to as far as I know, the AI data center may be only focus on about the counters at least. I'm not sure whether the transceiver or some other information. Maybe we can use the traditional method to upload that data.
Yeah, currently we were using JSON, which you mentioned that it's not an efficient way to do that, right? Pull information from the hardware and export as a JSON.
Oh.
So I was just wondering if we can.
Because the JSON format, we think it have too many useful character, so we didn't use the JSON format. Because as you know, the HyperX kind of have a lot of data, so some useless character it is not tolerant to us.
All right. Thank you.